I met Jack at Oregon State when we were both graduate students. He went off to the Naval Research Laboratory. I went somewhere else, and then I ended up at the Naval Research Laboratory. We keep bumping into each other. He's got his bachelor's degree in oceanography and mathematics from Humboldt State, a master's degree from Oregon State in oceanography, and then PhD is in engineering or
coastal engineering,
from University of Florida. So he's been all around. And then what else am I supposed to say? He's done cool stuff. So he was a Fulbright scholar, so he spent a year in the UK.
Right down there.
Thick beard. And then he's been at Delaware, University of Delaware since 2004. So I'm not going to say much more because I'm getting incoherent. Jack.
Well, thank you for having me. I appreciate the invitation. Should we dim the lights just a bit? Yeah, thanks. So Nathaniel asked me to come here, and I'm like, well, what should I talk about? And I thought I'm going to give you a little flavor for the more recent things I've been working on, but still sticking true to my roots, the stuff that I've been working on probably since before I even started my master's work. So today I want to talk a little bit about some interesting sediment transport concepts and measurements from two locations in the nearshore zone. And one of those is shown in a picture here, probably what I'm known for more, called the Swash Zone. So this is the area of the beach where the two lovers hold hands, walk off into the sunset, and the wave splashes their feet, which means great, we can get there really easily, but it turns out there's a lot of really complex physics that are happening here that make life difficult for us. It's a multi-phase flows that happen here, air, water, and sand. This is an excellent picture, I think, to demonstrate some of the complexities we might face. For those of you in the back might not be able to see, but up front this water looks pretty dark. That means there's a lot of material being suspended, and it's quite bubbly, quite turbulent, large changes in water depth. This is flow moving offshore rapidly and carrying a lot of sediment. So we want to try to understand the dynamics that are happening in this zone. And the other area of interest is the surf zone, near and dear to Nathaniel's heart and others in the room. And I won't go into a great detail here, but just to give a little bit of the motivation, the plot on the upper left has cross-shore distance on the x-axis, elevation on the y, and it's just some data I snagged from Duck, North Carolina, where really good morphology data sets exist. We don't need to go into the details of the plot, but the interesting aspect is this sandbar here, 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 here. It's bouncing around all over the place, so it's highly dynamic. I was remarking to Nathaniel that he has this same picture in his office. These are time exposure images. Give you some idea of where the sandbar might be located. In some instances, it's fairly linear and close to shore. Other times, it does really cool wiggly things. Other times, it's fairly linear and it moves offshore. And there are even other environments where you have lots and lots of sandbars. Nathaniel probably knows where that is. We used to go fishing out there. So today I'd like to talk about one type of sediment transport mainly, and it's called sheet flow. And I'll look at how we measure this component of sediment transport, and I'm going to show you some data from a macrotidal beach and from a large-scale laboratory study that we just concluded. I would be remiss if I didn't acknowledge all of my collaborators, but the two that are most important for the work today are the two PhD students who have conducted this work, Tace Lancrete, who's finished, and Ryan Mears, who has about a year to go. So let me carry on a little bit more with the motivation. In 2004, I organized an international workshop on swash processes where we got together and said, hey, where are the knowledge gaps? And there was a lot of them, but one of the key ones for us was how to measure this total load transport. So how to measure the transport of material that's happening close to the bed as well as the stuff that's being transported up in the water column. And we just had a second workshop in 2014, and we patted ourselves on the back for being able to do lots of these things. And one of them was indeed figuring out how to measure the total load transport, the majority of the talk today. The other motivating factor is sandbars. They're really cool. The problem that I see with sandbars is they're generally only studied from a morphological standpoint, meaning we make measurements today, we make measurements tomorrow, we look at the delta Z, the change in elevation or the volumetric change, without being able to measure necessarily the small-scale sediment transport and hydrodynamics that are happening. And why is that the case? Well, it's really hard to get the data. That's where the waves are breaking, making it difficult to get sensors in, and or sensors like to break under broken waves. Another issue is that bars move. So where do you put the sensors? You better put a lot of them out there, because if you put them on the sandbar today, that might not be where the sandbar is tomorrow. As far as I know, all the prior data for looking at sandbar dynamics in situ data was for suspended load transport, and those data sets are sparse. I say to even non-existent. I only know of a few, and if I'm wrong, you can correct me. These cool pictures have nothing to do with sandbars, but they're just cool, so I stuck them on there. Lots of interesting turbulence in these cool vortices. Anyhow, let's get on with the sheet flow. So typically when we think of sediment transport, we parse it out into something called bed load and suspended load, but there's this other type of transport called sheet flow, which is important under high stresses. And we normally look at these stresses based on a parameter called the Shields number, usually given the Greek letter theta, and that's a ratio of the bed shear stress to think about the submerged weight of a sand grain. So in cases where the Shields number is small, less than 0.05, nothing's moving. There's no sediment grains moving. So my sediment bed is stationary down here, and my concentration profile looks like 0 in the water column, and there's a discontinuity where it jumps to a packed bed. Now if we crank the shear stress up just a little bit, above 0.05, up to some critical value, let's say 1. Some people use 0.8. That's not important. We'll just use 1 for this case. We end up with the typical sediment transport regime that we normally think of. Bed load with grains saltating across the bottom, and then some material being suspended up into the water column. And our sediment concentration profile shows that. There's an increase in the sediment concentration near the bed, and then you see this roughly logarithmic decay up into the water column. Now if I crank that Shields number up even higher, again that critical value somewhere around 1, something interesting happens. We still have a lot of suspended load, but now we have lots of sediment moving right near the bed, and that's sometimes been likened to a carpet of sediment moving. Maybe on the order of 10 grain diameters, if you believe steady unit directional flow theory. We've measured up to about 100 grain diameters. So lots of material moving in a concentrated layer right near the bed. And that's the gist of what I'd like to present today. A difficulty for us is, or was, how the heck do you measure this? If you're looking at a regime that's only about 1 centimeter thick, what kind of sensor are you going to use that can handle being in a really energetic environment that can actually make the measurements? And it turns out there was such a sensor that could possibly be used, developed by the Dutch, called a conductivity concentration meter. And I thought, why not take that idea and make a profiler instead? So their sensor would measure at a single elevation, but I wanted to know what the profile looks like through that sheet layer. So we developed this sensor called the conductivity concentration profiler. It uses something called the 4-electrode approach. I'll show you what that is shortly. Unfortunately, we could only get a maximum sampling frequency right now at about 8 hertz based on the architecture, but we think we have a way to crank that up much higher. We're working on it now. The nice thing is I can get a 29-point profile with 1 millimeter spacing, so I can resolve almost 3 centimeters of concentration right near the bed. And of course, we tried to make this thing small because anything you stick in a packed bed is going to try to induce scour. If we do that, we're not measuring what we're interested in measuring. This is a shot from the beach. Here's 2 acoustic sensors measuring velocity when they're wet, of course, and then 2 of these conductivity probes that are buried from below sticking up. I will pass one around. If you break it, I don't care, because these things are basically throwaways. They're really cheap to make. The business end, which I'll show you in a minute, is attached over here, but it looks like a pipe bomb, so I didn't want to bring it for fear of getting tackled at the airport. And I'll show you what the parts of that are. So the bottom end that Dave's holding on to, that's the part that attaches into this pipe bomb-like area. This is the business end here with these sensors. Well, we didn't start out in this fashion. I had this idea way back when in 2007, and we built a really clunky analog model shown here. It was a proof of concept. We showed that it could work. We got a little bit of funding, and we started casting them ourselves in the lab, still analog. And we ran into problems. We were only using a 2-point approach, and we were having issues with electrolysis. So we said, we better go talk to smart people who've done this before. So I went and talked to some electrical engineers, and they said, oh yeah, we know exactly how to fix that problem, but you really ought to go digital and do it this way. So we talked with these guys, and that's when we came up with the current architecture. This is just a printed circuit board. We make the design, we send it off to a company. It costs about, about $800 or $900 to get the stencil made, and then those cost about $1 or $2 a piece. And then the board inside costs more than that, but that's why they're essentially throwaways. So in 2011, we ended up with this model where we made the housing in-house, and every now and then it would leak back here and fry your electronics board, so we thought, let's spend some money and have a really nice housing made. And that's where we stand now for the sensor. So let me explain to you how it works. We have multiplexers inside of there that are going to cycle through all these probes. So for right now in your brain, just think the first top 4 of those gold plates. Each of those gold plates is an electrode. And what I'm going to do is sample the top 4 plates, 1, 2, 3, and 4. I drive a current through the top, through number 1 and number 4, and I do that until I get a specified voltage between the sense electrodes. Whatever that current that I have to drive to get the specified voltage, that tells me the conductivity of the environment around my sensor. And if I can calibrate that conductivity to the amount of sediment in that volume, then that tells me the sediment concentration. And it works really well because even in fresh water, sediment is 3 orders of magnitude less conductive than fresh water. In salt water, you have a huge discrepancy between the two. So these are what the electrical field lines look like in clear water. Well, this is what it looks like in a sediment bed. I don't really care. So long as I can get the value out of my sense electrodes and I can calibrate it, I can tell myself something about concentration. And of course, we went and calibrated the sensor. So let me try to walk you through these figures. On the x-axis is volumetric concentration. So a fully packed bed would be out here like something 0.62. We can't get out that high. And then the vertical axis is the conductivity of the mixture, sediment and water, versus the conductivity of the fluid alone, just the water. And we're looking at really high concentration. So if you're used to dealing with data, possibly, from an optical backscatter sensor, you're working down here in this regime, maybe 100 to 150 grams per liter. We're working way out at 1,200, 1,500 grams per liter. It's really difficult to homogeneously suspend that mixture in water. So we went and found some liquid called lithium metatungstate. It's a heavy liquid. You can tune it to get the density to be just that of sand, and now I've got a neutrally buoyant material. Sorry, I've got a neutrally buoyant suspension of material. I mix it all up to try to get it homogeneous, dip the sensor in there and make measurements. That's the black line. And then I try to fit that with a curve. And there's 2 curves in the literature that suggest what this should follow. My pointer's dying. One of them's a linear law and the other one's a power law. Really doesn't matter which you use because the blue and the red line fit the data quite nicely and they're almost on top of each other. So all this tells me is that yes, I can use conductivity as a proxy for sediment concentration and that our sensor actually tells us what that concentration should be. And here's all the stats on it. There's a little more discrepancy here. This is a coarse sand, this is a finer sand. And when we were stirring it up, the material was sticking to the stir rod a little bit. So I think that's describing some of the problems on that side. Another aspect we need to consider with the CCP is a measurement volume. So if I have these 4 electrodes, they aren't sampling at a single point. They're really sampling over some odd shape and space. It really looks more like a peanut or a kidney bean. And we wanted to figure out what that size was. So we coded up a finite difference model to look at the current field around the sensor, in MATLAB of course, because why would you do other language? And this shows the horizontal axis and the other horizontal axis. So this would be the sensor sticking straight up. I'm looking at the plane coming into and out of the board. And if I use the theory from around a current field around a probe, usually we take that out to where the current density is dropped off to 1% of its maximum value. It turns out that contains 88% of the current, and that's how we guesstimate what this horizontal extent is. So in the horizontal plane, I have about 1.6, 1.7 centimeters in the horizontal. And you might think that's bad. I think that's actually good because that means I'm not looking at a binary switch where I have 1 or 2 grains popping into my area of interest. I'm actually averaging in the horizontal plane over a fairly large area. I don't expect that to change very much in the cross shore or the along shore of that small of a space. The bigger problem is what do we do in the vertical? Now I've got an issue because I want to resolve that profile in the vertical, but I have the same issue with I have some volume of interest. New pointer? Sensor. I have some volume of interest that I have to be concerned with. It's but I think it'll make it. So we had to come up with a way to check this, and we went back to our finite differences model. And what we did is we said, let's look at the model for a perfect interface. That's the green line. So essentially what I showed you when there was no shear on a bed. What does the experiment tell us, And the experiment was taking our sensor, putting it into a packed bed, and moving it up at about 0.1 millimeter increments and taking measurements. And what does the model tell us? That's the red curve. Well, both of them smoothed out the profile. If they were perfect, they would have given me a sharp interface, and they didn't. So that tells me my sensor has artificial vertical smoothing. That's bad if I'm trying to resolve the profile. But it turns out it's not that bad as long as the sheet flow thickness, the thickness of that carpet of sand that's moving, is thick enough. And so we can run the model in this scenario for different sheet thicknesses, so prescribed thicknesses of sediment moving, and then ask ourselves, what does the sensor tell us from the numerical model? So in a perfect world, it would all lie on this black line. So this is a perfect sensor. This is the actual sensor. And what you see is down here, when the sheet thickness is small, we're doing a poor job resolving it. But as soon as we get up to sheet thicknesses above about 3.5 to 4 millimeters, which is typically what we see, we approach this line asymptotically. So we use 3 millimeters as a cutoff. Any sheet thicknesses that we measure less than that, we toss out. We don't have any data. Anything above that, we believe, and we can apply correction to get it to where it should be. So that's the sensor. That's how it works. We have the only one in the world that exists, or we have the only fleet of them in the world that exist. And now we're going to use that sensor to make some unique measurements in the swash zone and the surf zone. And I'm going to give you an example from both of those. The swash experiment I talk about is not this experiment, but I love this picture so much I wanted to show it to you. If you look at this picture from about there up, you say, that's a beautiful sunny day at the beach. If you look at it from there down, you say, my goodness, what are these people doing? This was in February, 2 years ago now, for a project looking at post-storm recovery for one of my students. And there was a nasty storm. We put out this frame before the storm. What do you think the frame looked like afterwards? It was a mess. We had 300 pounds of cable that was all intertwined. We spent an entire day getting that cable undone. But we're resilient. We put the frame back out, put the sensors back on, and then a nasty ice storm came through. That's about 10 centimeters, and it's hard to tell from here, but they're all hanging at an angle because the wind is howling from one side to the other. I had a blast out there. We were in wetsuits in the water. It was great. But our real experiment I'm going to talk about today was in Perranporth, the UK, when I was on sabbatical. It's way down here in southwest England. And it only looked like this on that one day we were there because, you know, it always rains in the UK. So what we did for the experiment, we put another one of these, we call them swash rigs out there. It's just scaffolding pipe that we drive into the sand bed. And then out here we had what we call the swash rig where all of the sensors are located, sensors of interest. So this is what the setup looks like. I'll step through these one at a time. So we had 2 electromagnetic current meters. Those measure single point, the horizontal velocity, so just X and Y. 2 buried PTs, you can't see them because they're under the sand bed. We had 3 Vectrino ADVs, that's here, there, and there. Those measure all 3 velocity components at a single point at 100 hertz. We had a fiber optic backscatter sensor that measures a profile of suspended sediment concentration. We had 3 Vectrino 2 profilers. Those measure all 3 velocity components, but they measure a profile at 1 millimeter vertical bin spacing over 3 centimeters. So I can resolve boundary layer structure also at 100 hertz. There was a camera that was right there, but we took this picture before we put the camera on. I apologize, but I am going to show you some data from the camera. And we had 3 of our CCPs that we stuck. You can just barely see the business end of them. Notice they look offset. We do that on purpose because we don't know if the bed's going to go up or down. In fact, the bed bounces all over the place. That's an entirely different talk. I have slides in here if anybody's interested afterwards. So we cheat. We put the center one to split where the bed is now. We put another one lower and another one higher. So if the bed goes up or down, I could still try to get some data out of it. So let me show you some example data of velocity and concentration. This is about 10 minutes worth of data on the x-axis. Top plot shows the water depth. This is a macrotidal beach, 6-meter tidal range. That's great because we can put all of our sensors out when it's nice and dry, then sit back and drink a beer and wait for the water to come in, wet our sensors for 3 hours, it disappears, and we make our adjustments. This measurement snippet I'm showing you was probably closer to high tide because the water depth only goes to 0 in a few spots. So I'm probably closer to being in the inner surf zone, but that's fine. The next panel shows the velocity, with positive being onshore, and velocities ranging up to maybe 2 meters per second. There's a couple gaps in the velocity. That's because those sensors hang above the bed. As soon as the water depth falls below that height, I can't make measurements anymore. Next panel shows a suspended sediment concentration from several sensors. And the spacing here in the vertical is 0 to 400 grams per liter. And every time we have these strong offshore directed flows followed by an onshore directed flow, we get these dual peaked pulses in sediment concentration. That's sediment being picked up off the bed and carried up into the water column, or in this case being advected from offshore, advected past our sensors. And the sensors are separated by a centimeter, and so we have to guesstimate where the bed is, and it's going to be roughly where the signal saturation is, so it's probably in this range somewhere, but it's going to vary over time, of course. And the bottom plot shows the data from the CCP, and I'm only showing every other measurement. And the scale is different. Now it goes from 0 to 1,800 grams per liter, so a lot more material moving around. And what we notice is when we have these large suspension pulses, we also have large increases in the sheet flow concentration. What's most interesting is over here, where the bed appears to accrete based on signal saturation. See these flat lines? The bed appears to accrete, then it comes back down, and it looks like it erodes back down again. So where do I put z equals 0? Your guess is as good as mine on that one. But it turns out we can track where the bed is. So now z equals 0 isn't fixed in time. Z equals 0 is a function of time now in all of our future data analysis. And that's something we really ignored in the past because we weren't resolving these bed level fluctuations. So here's an example from one swash event that maybe shows the concentrations a little bit better. So 25 seconds. Most of the events there are infragravity driven, so you end up getting events on the order from 25 to 60 seconds. So here's the water depth, goes up to maybe 10 centimeters. The cross-shore velocity in black and the along-shore velocity in blue. So for this one, not much along-shore flow. Cross-shore velocity up to maybe almost 2 meters per second. And you'll notice again I lose the velocity here when the water depth drops below the height of the sensor. The next panel shows the sediment concentration as a P color. And the concentration is again in meters cubed per meters cubed or volumetric. And when the wave or the swash first comes in, we notice an initial drop in the bed level. So the bed level here as function of time is identified by the black line. The top of the sheet layer is